Hello, my name is James Wagner, and I'm a researcher at the University of Toronto. Today I'll be presenting my poster titled From Lab to Field, Tracing Seismic Tremors Across Scale, completed in collaboration with my colleague Karim Aboyana under supervision of Professor Giovanni Grazzelli. Our work focuses on understanding tremors and aseismic slip and their role as precursors to higher magnitude seismic events. By scaling laboratory observations to the field, we identify precursory signals of aseismic seismic slip transitions, enabling earlier detection of hazardous earthquake behavior and supporting proactive measures to mitigate well casing damage and operational risk. Let's start with the background. Fault creep refers to slow, apparently continuous fault slip, while seismic slip refers to sudden, high-velocity rupture. Both can occur on the same fault system and can each negatively impact nearby communities while also causing well casing damage and operational disruptions. The concern is that aseismic creep can gradually deform boreholes and compromise well integrity. At the same time, creep may load locked patches of the fault, nucleating a larger slip event, causing seismic activity that may disrupt drilling operations. An example of this can be seen in Figure 2, which shows how a natural fault within shale bedding can slip and cause borehole deformation. Seismic networks today can detect microseismic events and tremors, but distinguishing whether these signals actually correspond to dangerous casing deformation or to stress buildup on a locked fault remains an unresolved challenge. Our work addresses this challenge by linking lab-scale experiments with field observations to better understand the mechanisms that govern transitions between aseismic and seismic slip. To do this, we performed controlled laboratory experiments on pre-faulted rock samples. We applied different types of loading, mechanical, thermal, and hydraulic, to induce wide spectrum of fault slip rates. We used two key measurement techniques. First, digital image correlation, or DIC, to track full field displacement and strain. This allows us to see how some fault segments creep while others remain relatively locked. Second, acoustic emissions, or AE sensors, which capture the small seismic signals associated with microfracturing and slip transients. These signals can be transformed into spectrograms for frequency analysis. If you look at Figure 3, you'll see our laboratory setup, including the DIC system, a high-speed camera, heating platen, AE sensors, and the loading system. Together, these tools let us measure how fault slip evolves in both space and time. To compare lab and field data, we use the widely adopted ACI scaling law that relates the frequencies observed in laboratory AE spectrograms to those measured by seismic networks in the field. Frequencies in lab and field showed consistent scaling with the fracture dimensions in our laboratory samples and kilometric scale field faults. This allows us to link small-scale experiments directly to real-world fault systems and understand field deformation through lab tests. Moving to the results, displacement and strain analysis. The results shown here are from a thermal gradient-induced seismic event. The sample contained a pre-existing fault, and when thermal loading was initiated, we observed the nucleation of a macro crack that triggered creep along the fault. Over time, this localized slip propagated into a larger macro crack, effectively dividing the fault into creeping and locked segments. This evolution is evident in the DIC analysis shown in Figure 4. On the plot, the x-axis represents distance along the fault, the y-axis represents time, and the color scale indicates slip magnitude. Up until approximately 750 seconds, the fault remains locked, as shown by the vertical bands in the analysis. After this point, the nucleation of the macro crack initiates slip, seen as a linearly increasing slope of displacement. This process partitions the fault into creeping segments, shown by the diagonal displacement bands on the left, and lock segments, represented by the near vertical bands on the right. A similar pattern is observed at the field scale, as shown in Figure 1, where the San Andreas fault accommodates different rates of creep. This behavior is directly analogous to the coexistence of creeping and lock segments observed in the laboratory. As the macro crack propagates, stress shadowing effects accelerate creep along the fault. The increasing deformation further loads the lock segment, creating a nucleus for seismic slip. This transition is captured in Figure 5, which shows the rise in friction coefficient as the macro crack approaches the lock segment immediately prior to rupture. The key takeaway here is that accelerating creep can both partition the fault into domains by inducing off-fault fractures and create stress concentrations that set the stage for seismic slip. The second set of results comes from the spectral analysis. As creep accelerates, the acoustic emissions data revealed detectable tremor-like activity, which appears as distinct spectral events at both the laboratory and field scales. This is illustrated in Figure 6. In the laboratory test shown above, there is a clear increase in the number of tremor-like events as the creeping segment accelerates, continually loading the adjacent locked segment until seismic rupture occurs. At the field scale, we observe analogous behavior, such as the volcanic tremors recorded at Mount St. Helens prior to rupture. This accelerated creep, accompanied by tremor activity, is also captured in spectrogram analysis as low-frequency bands over longer time windows. These are shown at the laboratory scale in Figure 7 and at the field scale in Figure 8. In both cases, the spectrograms revealed distinctive low-frequency bands that precede larger slip events, providing a clear spectral signature of the transition from aseismic to seismic slip. Together, these results demonstrate strong consistency between laboratory experiments and field observations, suggesting that precursory tremors identified in the lab can be used to interpret seismic monitoring data in real time. So why does this matter? From an industry perspective, the ability to detect and correctly interpret precursory signals to seismic events makes it possible to identify patterns of aseismic creep that can deform well casings and mark the onset of creep-slip transitions, which may escalate into larger seismic events. By scaling laboratory precursors to field observations, this work can help reduce operational risk by providing operators with a framework to recognize hazardous slip behaviors early, allowing for the implementation of proactive measures to safeguard infrastructure and maintain production continuity. Thank you.